Okay, hey, how are you? And welcome to this tutorial regarding the major project for the manufacturing engineering. So actually, this slide has been used for many years, and when I came back to the tutorial, I found out the same mistake can be found here. Uh, Now we're talking about the model of the pump we are looking at. Actually, if you go and check the brand is going to be the same, the Power Auto. The model number is going to be PUKS 85R, not 50R. Now, the difference between the 50R and the 85R is going to be about the flow rate we're going to have for this pump. So just remember that. I'll try to update the file. Uh, and actually, again, to try to mention that multiple times. Try to send you an, um, an email regarding the type of the pump we have in the lab. Okay, now the one we're talking about is the purple one, not the silver one. And the dimension I'm going to talk about in this example is going to be the same one, which is going to be used in your report. So first we need to check what is used for. Now the hydraulic pump in general, it's called hydraulic pump. Sometimes we call it the gear pump. This will depend on the either classified depending on the material we are going to pump it with, or depending on the working principle. So the working principle of this pump is having two gears, the drive gear and the driven gear are going to rotate together, generating two areas of pressure within the pump, and thus we're going to have positive and negative pressure area, and thus the flow of the hydraulic is going to be achieved. Usually, these types of um, pump is made of the cast iron, so it's going to be gray cast iron again, something similar to the one we use in the manufacturing of the engine block. And we're going to talk about this one later. What's used for money application is going to be applied the use of this type of pump, like for example, how to move the crane. Usually we need to use the hydraulic power. And this hydraulic power require pressurizing the hydraulic oil. And this can be only achieved by using the gear pump. Same thing is happening in the garbage truck. We need to have a power to move this piston and achieve very high pressure to have a higher force to compact the garbage. Same thing here in the hydraulic press, how to actually we are going to have the hydraulic tank, and this hydraulic tank is going to have a pump somewhere here, and this pump need to connect of course to a motor by rotating the gear, the driving gear, and the process will happen. We're going to pressurize the pressure inside the cylinders and the piston, and boom, we're going to have the magnified power to force to compact the thing. Now, what are the materials of the main components we have for this pump? Now, you can actually take this photo and use it in your description in your report. As what you can see here, that we're going to have the external part, we're going to be the casing. That's the casing of the pump. We do have the head. Okay. Usually these are going to be made from the iron or the gray cast iron. Sometimes we can use steel, sometimes we can have the high alloys, and sometimes we can use the composites. But I can send you later a video which can show you that some parts, some pumps, but not this model, can be made of aluminum as well. For the internal parts like the shaft we have here, usually going to be made of the steel or using the high alloy if you require to have higher power. Other things like, for example, these two plates, we call them the pressure plates, are made of the aluminum. We have these bushes, and actually this bush is going to be made of the steel, but we usually going to coat them with a Teflon. So the Teflon is going to absorb some hydraulic, and this will prevent the process of the dry startup for the pump, and thus we're going to save the shaft surface. Others like the bolts and not the bolts, usually the studs we have here, different materials. We have the off-shelf item like the seals and the rings and more seals, of course, you can see here. What else do we have? The shaft seal, we talked about that, the backing and the lip seals. In which direction does the drive gear will rotate to? Now, usually, this is a different model, but the principle are going to be the same. So what we have here, we're going to have two ports. We have the suction port and we have the pressure port. The suction port is going to be the inlet and this one is going to be the outlet. So usually the rotation of the drive shaft is going to be, in this case, if we look from this side toward the pump, take a look on it, it's going to be on the counterclockwise. And what will happen is that when this one, once again, I'm talking about, I'm looking from this side, okay? So it's going to rotate in this direction. So it's going to take the oil from this point and take it to that point. So direction is going to be clockwise from here, counterclockwise from the other side. I'm talking about the other counterclockwise because that will be the drive shaft direction. That's the most important thing for me. Okay, so the other shaft or the other ideal gear is going to follow the movement of the driver gear is going to rotate in that case from the other side on the clockwise and thus again to rotate in opposite direction, generate the negative pressure area here and positive pressure area on the other side. Thus we're going to have the pressurized flow of the oil to occur. So it's usually going to look something like that. Okay, so one of them is going to be drive gear, the other one is going to be driven gear, rotating, taking the hydraulic from the inlet port, push it toward the outlet port. Now just imagine if again to make a mistake and again to do the rotation of this one in the opposite direction. Okay, if I can do that in the opposite direction, it's going to bring the pressure from here. Here we're going to have negative pressure, and we're here we're going to have the positive pressure. So this will push back the oil on the opposite direction. So what the material of the thrust plate and why this material has been chosen, simply we said that the thrust plate is actually is made of the die cast aluminum, the aluminum. And the thrust plate is going to be consumable item. Now, what do you mean by the consumable item? Again to send another video after that, which is talking about the actual pump. We explained that on in the lab last week. And what's happened is that we're going to have the gears. They're going to be sitting inside the main body of the gear, and we're going to have friction between the shaft and the main body. So I don't want to damage the main body. I don't want to damage the shaft because the time consuming and the material, the process of the manufacturing this shaft are going to be quite expensive and the material is quite hard. The same thing is going to be for the main body. So instead of damaging these two things due to the wear, due to the friction we have between the two main parts, I can sacrifice something in the middle, which is going to be the thrust plates. So thrust plates is made of aluminium, which is going to be a softer material. So we're going to damage the thrust plates instead of damaging the main body of the gear pump. And so to make an overhaul for the pump, I only need to change the thrust plate from time to time. Now, why one port is larger than the other? Simply to avoid the cavitation. The suction port is going to be the larger one. This answers your question here. So the cavitation means we're going to have some bubbles. If we're going to have very small, something like when you try to drink the bubble tea. So of course, if we're going to have the smaller straw, this will be too hard to take the things if the fluid is quite thick, and this will cause some bubbling within the fluid, and this, of course, going to cause the vibration to be happen to the pump itself. And this vibration, by the way, is too dangerous. Sometimes can cause an explosion of the pump, if we're going to have the resonance uh, phenomena. Also, it's going to, of course, pumping bubbles, and this will reduce the efficiency of the pump itself. And also, it can no longer build the same head because it's pushing the air all the time. Now, why does the pump have to be manufactured to very close tolerances? Now, we said these types of the pump are going to be supported on both sides, external and the external gears pumps are going to be used for the higher pressure application. So when we talk about higher pressure application, we're talking something about the let's say above 50 kilopascal for a small area. And also for the velocity, we're talking about something in the range of the 1,750 to 3,500 RPM. And of course, this will be a very high speed in the rotation. So if again to have any misalignments for the dimensions, once again we're going to increase the rate of the wear, and also again to have some vibration, and this will cause a damage for the components in a very high rate. The advantage of having the uh, close tolerance is going to achieving high speed, achieve high pressure, no overhang of the bearings loads, relatively quiet operation, and also design will accommodate a wide variety of materials. The disadvantage of having that's we are going to have four pushing in the liquid area. No solids are going to be allowed because the dimensions are too close to each other, mainly for the gear. And also the fix and the clearance is going to be two critical dimensions. So which dimensional tolerance are going to be the critical? The first important thing is going to be the gear shaft. And when we talk about the critical dimension, it's not only about the shaft, the area itself, also about the gears. And once again, I show that in the lab when you actually try to contact the gears together. And actually, this can be happen with any types of the gears, like for example the gearbox in the car. So when you try to uh, make gears in the design processing, usually you try to avoid the well, I call it the try to reduce the contact area between the gear teeth on both sides, the driven gear and the drive gear. Or that's simply because we don't want to have more losses due to the friction between the gear teeth. So reducing this area is going to be optimal thing, but once again, it's going to cause a losses in the forces transformation between the two gears. Also, the other two critical dimensional area is going to be the bearing and the dowel position. Okay, so the gearing is going to be, well, we cannot see this one from this side, but I'm going to show you that in the video I'm going to post with this one. Actually, we are going to have very critical dimensions where we need to fit the pushes inside in the bearing holes, and this also should not compress the bearing size. Okay, and the same thing is going to be for the dowels. So the dowels can be simply fitted by a light press fit inside the dowels holes. The dimension of the dowels itself should be actually a very high critical dimensions. And we're going to talk. Actually, we talked about the process of how to achieve very high tolerance, dimensional tolerance for the holes by doing the drilling, the boring, and then we need to do the reaming. So we are going to achieve the exact dimension we are after. So how the bearings are going to be lubricated? And now we said that this bearing actually are going to be made of steel, but it's going to be coated with the Teflon. The Teflon again to have the ability to absorb amount of the hydraulic and save it for the next run. So what's happened is that we're going to have a moistured Teflon material layer, and when we're going to start the pump on the next time, the contact area between the shaft and the bearing from the inside is going to be wet, not dry, and thus we're going to avoid the dry starting, and thus we're going to have a longer lifetime for the bearing shaft. What are the dowels used for? And now, in general, the dowels are going to be used for the alignment of the two pumps. So we don't have to look for the exact dimension. That's a process going to help a lot in the process of the assembly of the pump. So we will always going to find the direction and how to put the bolts on the next time. Just imagine that if we don't have this one, so we need to find the location of the hole here, for example. If I would like to insert the bolt, I need to keep looking for the threaded hole through the cab hole, and this will take some time. We usually try to reduce the time for the assembly, so putting the dowel is going to reduce this time. Now, the hydraulic in general, you'll study that in the fluid dynamics. So actually, the concept is very simple. Something like what you have in your uh, the hand pump you are making, you just pressurize and release. So something like expansion and compression multiple time. Now, if I get to use a difference in the diameters, I just try to summarize what we have in the next two slides or three slides. If I'm going to put a pressure in a smaller cylinder and send that to another cylinder through a pipe, which is going to have a bigger diameter, the pressure is going to be the same. But what will be different is going to be the forces, mainly because the diameter of the piston I'm pressurizing is going to be different. So I'm going to show you that on the next slide. So all based on the theory of the Castelli, the Pascal, and John Lewis Mary Boselli. So the fluid power is a very simple term. I'm going to show you the next photo. I don't worry about that one. Okay, now that's what we're talking about. So the process is very simple. If I get to put pressure by using this piston on this area, which is going to be equal to 100 kilopascal, the pressure at any point in this fluid is going to be the same. So the pressure itself is equal to the force one divided by the area of the piston one. That's obvious. The pressure is equal to the force divided by the cross-sectional area. So I achieved the required pressure at that point by using a smaller force on a smaller area. Let's say it's going to be 100 Newton divided by 0.001 square meter to achieve a very high pressure at that point. Now, the pressure at this surface is going to be the same. That's what will happen inside the fluid. That's the magic of the fluid. So, for example, the same pressure is going to be distributed over this surface. If I going to multiply this pressure by this surface area, again to find the value of the force number 2. So what happened is use small force on small area, I'm going to achieve a larger force on the other side because the area of the piston has been increased. Now, for the chosen pump, we need to choose the following operation parameters. How can we find the code? How can we read the code of the pump itself? So the PWO is the pump series. The O is going to tell you about the rotation direction. So the O is going to be the opposite to the engine, or the S is going to be the same as the engine. So if the engine is rotating clockwise, the shaft is going to rotate clockwise. Or we can design it to be the opposite. In that case, we will need to use a gearbox. And the 90 is going to tell you what the flow rate at 1000 RPM. So the 90 obviously is going to be mean 88 liter per minute at 1000 RPM. 25 mean 23, 35, 34, and so on. Okay, so you need to look at the model And the motor I'm going to have is going to be something about, I think it's going to be the 85. So you need to, let's work on, we're going to have this example regarding the power required to run the motor. The data we have are the following. We're using the terms of the common to the mechanics, which is going to be that the power of the hydraulic is going to be equal to the delta P, the pressure difference, multiplied by the Q, which is the flow rate. So the delta P is going to be pressure difference across the pump in Pascal. The Q is the flow rate in cubic meter per second. The power of the shaft is going to be equal to the torque of the shaft multiplied by the RPM value. But this one is going to be in radian per second, not review per minute. And of course, you will know how to make a conversion between both. So first, let's calculate the flow rate in cubic meter per second. We have 60 seconds in 1 minute, and we have 1,000 liter in 1 cubic meter of fluid. So the flow rate we have from the data sheet is 34 liter per minute. So to find the value of the Q, again, to use the 34 divided by 60 seconds multiplied by 1,000 liter per cubic meter. And thus the units here is going to be the L will be simplified with the L. The minute will be go with the minute. We're going to have second instead. And thus we are going to left with cubic meter per second. Now, of course, what we are going to have in denominator here is going to be seconds over cubic meter. When I'm going to reverse the thing upside down, we're going to have cubic meter per second. So that's the calculation. 34 liter per minute divided by 60,000 is going to be equal to 0.00566 cubic meter per second. So we got the value for the Q. Step number 2, delta P. So delta P is going to be 31 million Pascal. So the power of the hydraulic is going to be equal to 31 million Pascal multiplied by the Q value we got, which is 5.6 multiplied by 10 up to 4 minus 4. And thus the power of the hydraulic is going to be equal to 17,360 watt or 17.36 kilowatt. The power of the mechanic or the the motor itself. So we consider that we have the efficiency of 70% for the motor. So to achieve this amount of the power to operate the pump, I need more than this power because the motor itself is going to have a losses, and this loss is about 30%. So the pump I would like to use should have 30% more than this power. So to do that, I either can do either way. The power 17.36 divided by 0.7, which is going to be equal to 24.8 kilowatt, or is going to be the 17.36 multiplied by 1.3 is going to give you the same feeling because I need 130% more than the power required to run the pump. So the power required is going to be 24.8 kilowatt. Let's say it's going to be 25 kilowatt. Later you can do the rest of the calculation to find the value uh, of the what was the other thing? The torque. What was the other equation? Okay, yes, the power of the shaft, which is going to be the torque multiplied by omega. Well, now we know what the power of the shaft is, which is mechanical power. We know the RPM value is equal to 1000. Try to calculate that in radian per second. Then you can find the value of the torque in Newton meter. Okay, some of the useful resources to do the calculation from this one can be found in the following references. Now, what do we have on the university website for this project? So the first thing we have is this document, okay, the major project of the gear pump. So the task mainly is going to be the study of the power auto gear pump provided in the lab and its component. and to investigate how to fabricate the product. So each student need to organize his or her written project report individually. So this work is going to be individually, and by addressing the criteria of the marking criteria for the project report of the available on the UTS online for the manufacturing engineering. The following points may be considered. First, which kind of the pump you are studying and what is used for. What are the material of the main components? What are the materials of the thrust plates and why this material has been chosen? How does it work? Why does the pump have to be manufactured to such close tolerances? Which dimensional tolerances are going to be the critical? For which choosing pump, we need to choose the following operating parameters. Once again, we look at 85 liter per minute. So we're looking at the type 85. And the maximum power is given at 310 bar or 4,500 psi. You need to find out how to change that into a Pascal. The efficiency assumed is 80%. Discussion about the material, you need to calculate the shaft power and the driving torque. So I told you how to find the driving torque, and I show you how to calculate the shaft power. I'm going to explain that on Tuesday lecture anyway. Discussion about the material wastage in the driver gear, outline the manufacturing operation that you have decided, and the workflow of the material through the possible factory. And it is suggested that you consult a pump reference book to find more general information on this type of the pump, and this will be a useful to extractive components of your reports. What do you need to hand in? Once again, we need to submit individual written report, and there's no instructions or the limitation of the page number. As references, 20 pages may be suggested if you're going to use the A4 paper. How to submit through the UTS online electronically. When to submit, you can check the due date using the UTS online spreadsheet. Uh, Other available items are, first, we can see that this will help you to do the calculation for the pump. So the first thing we can calculate is going to be the material wastage when the machining the driver gear. So the steps available here are, we need to measure the driver gear, determine the volume of the metal in the gear by displacement water. Don't do that. Select available bar assuming the cylindrical blanks are position bands sold from the AISI steel grade of the 4340H bar stock, allowing for the surface wastage and the end loss. Determine the suitable blank diameter and the length and calculate the blank volume. Calculate the metal wastage as a principal of the material supplied and the percentage of the finished product. So what you need to sketch here is going to be just a simple sketch diagram of the shaft, which is going to be something similar to what we have in this engineering drawing. So we're sketching something like that. You can see that multiple rectangular shapes. These are the dimensions we have. So the total length is 202. That's mean I'm going to say that the shaft I'm going to use, the original bar I'm going to use is going to be, let's say, 210 millimeter length. The maximum diameter we have for this shaft is going to be for the gear section, which is going to be something about 57 millimeter diameter. Okay, 57 millimeter diameter. So by simple research, you will find that the standard diameter we have for the blank material is going to be about 60 millimeters. And thus we need to remove about 3 millimeter out of the diameter of 1.5 millimeter from the radius. And that's what we're going to show by the machining in the next stage. So I will say that the cylinder again to use at the beginning is going to be 210 millimeter length and the diameter of 60 millimeters. Bingo. I can now find the volume of the original part. Now let's try to make the calculation. Now the grade of the steel I'm using is 4,340 H hardened steel, and I'm going to search for the density of this type. Okay, so just write down density. I'll tell you why we need that. So the density of this part is going to be something between 7.7 to 8.03 kilogram per cubic meter. So let's take the average, and let's say it's going to be 7.8 kilogram per cubic meter. That's the density. Now I will go further. Okay, not on this part, sorry. Okay, so now I know the density. I have the actual part is a cylindrical shape with the diameter of the base of 60 millimeter and the height of 210 millimeters. So I can find what will be the mass of the original part. Now, of course, I can calculate the volume and I can calculate the mass. Now, for the other part I have, which is the shaft itself, I'm not going to bring water in the lab. I don't have to do the measurement of each single part and do the calculation for the volume. What I can do is put this part on the scale, find its mass. If I know the mass, I know the density, I can find the volume. The mass of this part is going to be 1,557 gram. So if I'm going to divide that by the 7.8 kilogram per cubic meter, I will be able to, not divide it actually, I can find what will be the volume of the shaft I have. So I know two volumes now. I can do the calculation and find out what will be the mass of the wasted material. I can find the change in the volume we achieved from these processes. So I can do the percentage of the material now. Okay, so that's the calculation for the first part. Now the rest of the drawings we have here are going to be for the pump case, and also I have the drawings for the head. Now the head and the case were made by the cast iron, the sand cast iron, and for the shaft, obviously it was made by uh, machining. We're going to discuss the machining approach we have for this part, but simply because most of the part is cylindrical shape, so it's going to be done on the lathe machine. And I think I showed you a video for the uh, double spindle machine. This can be an alternative method for doing the work. But for cutting the spline and cutting the gear shaft itself, this gear itself has been made on the milling machine, or we can do it by the hopping process for the gears. For this one, for the supply, it can be done by, for example, the once again, it can be done on the milling machine. Actually, I prefer to do that. To cut the gears on the milling machine, we need to use the indexing device, which can divide the circle into an equal uh, uh, parts, not equal angles, is equal parts. Usually, the shape of the teeth and the dimensions or the pitch diameter are all going to be a standard item. So you can find about this one from the by doing a simple research. Okay, so I think that's it for this tutorial, and I'm going to post it online. Beside that, you are going to be able to watch the video I explain the, the gear pump itself in the lab, and we're going to have further discussion after the lecture on Tuesday. Thank you for your listening and hope to see you soon.